don't forget when you're off doing whatever other things you want to do. And if you're in lab, you've got something to do before you leave.
Great.
So don't
I don't know what
forget
you're talking about.
The link you sent me from PD.
Oh, it's in your lab.
Yeah.
Yeah, yes, yes.
It was
This is
in
having
the-
to look.
I can't remember if it was you or Michael, but you guys sent it to me on the chat.
Okay. Lecture and transport chain today. One complex at a time. Complex one. This is the NADH coenzyme Q oxidative phase. This passes electrons from our carrier. Passes electrons from NADH to coenzyme Q. It contains a flavin mononucleotide. That's abbreviated FMN. It contains iron sulfur clusters. And it can be 2 and 2 or 4 and 4. And transfer of electrons results in proton translocation. So this is 4 protons per NADH. From the matrix to the intermembrane space. And these are transported by a proton wire. Which consists of ionizable side chains. And possibly water. And what happens is that the redox reactions, as those electrons are being passed, cause conformational changes. In the complex that alters pKa's. And that promotes your proton transfer. Okay, so we're at the first complex. So, complex 1, NADH is going to pass its electrons to complex 1. They're going to eventually pass them within enzyme Q. back to this table. We'll come back to this table several times. This just lists all the different redox centers that are in the complex. So the complex 1, there's the flatten mononucleotide, and then there are all of these iron sulfur centers. And those iron sulfur centers could be 2 irons to 2 sulfides, and then you're coordinated by cysteine side chains. Or it could be 4 irons, 4 sulfurs, again coordinated by cysteine side chains. And I think you've seen those before. Not too long ago. Majority wins. Conatase. So what was the iron sulfur complex in a conatase doing? Remember what its role was?
The coordinated carboxyl thing.
Yeah, so you
The
needed
proximity.
it to hold the substrate in place for a conatase. But not for redox. But here, now we have something that's needed for redox. How are these things going to help electrons move around?
Accepting electrons.
Yeah, that would help. It brings up some electrons. So how many charge species are there for iron? Most common ones?
2
Plus 2 and
plus 3.
Okay, so iron is great at passing 1 electron around. So iron 3 can take an electron, and iron 2 can donate an electron. So you find lots of these iron clusters in our complex systems. Oh, I'm going to show you one more. So iron is only going to pass 1 electron at a time. That's all it can do. Our flavin mononucleotide, this is our FN, and this is the oxidized form, and it can accept 1 electron to make a free radical, or it can accept both to make the reduced form of the FNN, so it can pass 1 or 2 electrons at a time. And then coenzyme Q, which is our final destination at the end of complex 1, same thing. It can accept either just 1 to make the semiquinone, which is the free radical version, or it can take 2 to be fully reduced. Okay, not structures you need to memorize and everything like that. But you do need to know that it can accept 1 or 2 electrons. Okay, so that's complex 1. Oh, sorry. One more slide. Alright, so here we are, complex 1. So our NADH comes in, we're going to pass those electrons around, and then I end up transporting protons across the membrane. So this is from the matrix to that intermembrane space. And as through proton wires. These things are just transmembrane proteins where you've got a bunch of little charged side chains. So they make arginine, aspartic acid, aspartic acid, and they just trade protonation states. So you have something that is, so if this were our matrix side, you have a proton out here that protonates an aspartic acid, but if it was already protonated, it would pass its proton onto here, which causes that one to pass its proton on. And so you just shuffle the protons down until you end up on the other side. Now I can go back to the notes. Complex 2. this is succinate. Coenzyme Q, oxidase reductase. This is going to pass electrons from succinate to coenzyme Q. And this is via succinate dehydrogenase, which we saw where? What pathway? Citric acid cycle. And what is the carrier for those electrons? Okay, FADH2. So this is our entry route for electrons coming from FAD. So it's not like this thing moves around. The complex is just there in the membrane, in the inner membrane, and it participates in the citric acid cycle, and it participates in the electron transport chain at the same time. So the complex includes the CAC enzyme and its prosthetic FAD. It also includes iron sulfur clusters. And a cytochrome. Happens to be a cytochrome B. I'm not going to really worry about having to keep straight all the cytochromes, but it's a B560. And this is just basically a protein. A cytochrome is a protein that contains a heme, which means that we talked about those before. So what other protein have we seen in the past that contains heme? Hemoglobin. Okay. What is it in hemes that can accept electrons? Iron. Okay. So there's an iron center that can transfer electrons as needed. Another thing to note about this particular step is that there is no proton transfer at this step. And again, this is why FADH2 provides less ATP than an NADH. Our electron acceptor at the end is coenzyme Q again. So this is where complex 1 and complex 2 both dump their electrons. Okay. So we have electrons coming from NADH. We have electrons that are coming technically from succinate. Because that is where we get the electrons to reduce the FAD. And then I'm going to, from that FAD, pass it through a bunch of iron sulfur clusters, pass it to a heme, and then eventually pass it to coenzyme Q. Okay. So now we have electrons from NADH and electrons from FADH2, both at Q coenzyme Q. Oh, I don't know how many slides. I had a lot of slides today. Hemes, cytochromes. So cytochromes, again, are just proteins that contain hemes, and there are 3 types, A's, B's, and C's, that we're going to see. So B is the one that is in complex 2. Again, the structures, I don't care that you know one heme from another, except that you should be able to recognize the heme when you see it, as that program immune system. And then there's that ion coordinated in the middle with those nitrogens. I have to look at the next slide, okay. All right, so number 3. Complex 3, this is the fun one. This is why you came today. Coenzyme Q, cytochrome C, oxidoreductase. This passes electrons from coenzyme Q to cytochrome C. Contains an iron sulfur cluster. Hemes, and this can be both B's and C's. And it's a kind of a 1 electron at a time thing. So cytochrome C can only accept 1 electron. So you have 2 electrons from coenzyme Q are passed 1 at a time to 2 cytochrome Cs. The Q cycle. And this is going to result in proton translocation again. We're going to write out the equations, and then we'll look at the pictures. It's a Q cycle. Cycle 1. Coenzyme Q, and some books they put H2 to show that it's reduced. I'm just going to put a little R&D to say it's reduced more. Plus the cytochrome C1. So it varies more than one cytochrome C. The final destination is cytochrome C, period, but there's a C1 involved. And at this point, the cytochrome C initially is going to be in its oxidized form. So the iron in the heme is a 3+. What I'm going to make after the first cycle is a coenzyme Q free radical which is called the semiquinone. Plus the reduced cytochrome C. So this is an Fe2 plus. Plus 2 protons, and if the balancing thing bugs you, the protons were on the reduced coenzyme Q, actually. So these are released into the intramembrane space. So then comes cycle 2. And we bring in another coenzyme Q reduced, plus the semiquinone, plus another cytochrome C1 in its oxidized form. Plus 2 protons that are from the matrix. And all that is going to go to form a coenzyme Q in an oxidized form. A coenzyme Q in a reduced form, another cytochrome C1 in its reduced form, so 2, and then 2 protons that are released into the intramembrane space. So my overall cycle, we just add those together and start canceling some things, is a coenzyme Q in the reduced form, plus 2 cytochrome Cs in the oxidized form, plus 2 protons in the matrix, that then go to the coenzyme Q in an oxidized form, 2 cytochrome C1s in the reduced form, and 4 protons delivered to the intramembrane space. Cytochrome C1 transfers single electrons to the regular cytochrome C. And then cytochrome C is the intermediary between complex 3 and 4. Very good picture. to our chart. Here we are with some coenzyme Q that has electrons, and we're going to pass them through complex 3 with our Q cycle. And so again, there's some hemes, there's an iron sulfur cluster, there's this cytochrome C1 that has my heme C1 on it, that will eventually deliver it to cytochrome C. Here's the easy version of the cycle. So coenzyme Q, and this is my little cycle because I'm only going to pass one electron at a time. So coenzyme Q has 2 electrons right now in its reduced form. But you can only pass 1 electron at a time to cytochrome C because an iron can only accept 1 electron at a time. And then the cytochrome C, 1 electron at a time. And in the process of that Q cycle, per electron pair, we're going to move 4 protons into the intermembrane space. Okay, so this is the Q cycle. Coenzyme Q is kind of weird. If we have to go back here, it's just showing you as a circle. This thing can actually move back and forth across that intermembrane. It's embedded in the membrane, but it can kind of move towards either side of that lipid bilayer. Whereas the complex is fixed as a big transmembrane complex, but Q can diffuse. And so that helps a little bit when trying to understand this figure. So this is my matrix side, the blue is the membrane, and then this is my intermembrane space side. And I have reduced coenzyme Q here, so it's showing H2 that it's reduced. And it says from complex 1, but that also could be coming from complex 2 as well. Okay, so here is showing this that it's diffusing across, and it's going to give up the protons and the electrons. So the protons end up just being put into that intermembrane space side. The electrons get split between the quinone, so I keep the semiquinone free radical, and then 1 electron, this is an iron sulfur protein, so this is where my iron sulfur cluster is. So 1 electron goes to the iron sulfur cluster, that then is moved on to cytochrome C1. The quinone has to go back to the matrix side. And free radicals react with everything. And so you can't just have the quinone diffuse back as a free radical, because it won't keep that electron. It will react with something. So instead, the quinone gives up that electron to a bunch of other hemes. So we have a B there, and another B. So it just passes it to this one, the electron passes it to that one. And then the oxidized form of coenzyme Q can diffuse back across, and then it accepts it back from that last heme. Okay. So now I still have my little free radical here. That's the first cycle, so that's 1 electron delivered. Now I have to bring in another reduced coenzyme Q, so this is a different one from that one. So this is the second one that comes in. Same thing, it can diffuse across. It's going to give up its protons to intermembrane space. It's going to give up 1 electron to the iron sulfur cluster that ends up on cytochrome C1. And then I have the same problem. I have this little semiquinone that can't get back across with its electron. So it passes the electron to a couple of hemes, and then the oxidized form of the Q diffuses back to the other side. And when I'm here, notice that there isn't any interaction going on like there was there. When I'm here, that oxidized coenzyme Q then is ready to accept more electrons from complex 1 or complex 2 to get reduced again. My semiquinone, another coenzyme Q that ends up being a semiquinone from its oxidized form then can be turned back into a reduced form. So that's why even though I have 2 reduced quinones coming in, since 1 reduced quinone comes out at the end, that cancels on both sides of the equation, so it looks like 1 reduced one comes in and 1 oxidized one comes out in the net reaction. So that is the Q cycle. End result, we get 4 protons on this side, and then we get 2 cytochrome C1s that get reduced, so that we get 2 cytochrome Cs reduced from 1 NADH, or 1 FADH2. Was it worth coming to class today?
I'm still lost.
Okay.
Yes, please.
Complex 4. This is cytochrome C oxidase. So this passes single electrons from cytochrome C to oxygen, which is our final electron acceptor. And this includes 2 hemes, or hemes, and a couple of copper centers. What are my oxidation states on copper? +2 and +1. Yeah. So kind of like iron, I can have 2 different oxidation states. So copper can be in +1 or +2 form. It requires 4 cytochrome Cs in a reduced form to reduce 1 oxygen molecule. So this one, the reaction is 4 cytochrome Cs in reduced form, which is an iron 2, plus 4 protons. And these are matrix protons. Plus an oxygen, which is also found on the matrix side, goes to 4 cytochrome Cs in the oxidized form, plus 2 waters. This step also involves proton transfer. So 4 protons on the matrix side are transferred to the intermembrane space side. That's a different 4 protons from those. These are on the matrix side to begin with. They are consumed to make the water, but that's still on the matrix side. So it involves reduction of the proton ion concentration, or I should say reduction, a decrease in the proton concentration on the matrix side, which is good for us. We're trying to make a proton gradient. But the transfer from one side to the other is a separate 4 protons from those. Okay, so we are at our last complex. So here we are, cytochrome C has the electrons, but each cytochrome C only has 1 electron. Complex 4 has a couple of hemes, has some copper centers, and we're trying to deliver those electrons to oxygen. So again, we're right here, cytochrome C, we're going to pass through copper, pass through cytochrome C, pass through another cytochrome, copper complex. And then eventually, we're going to add it to water. So here it's showing electrons being passed to half an oxygen to make 1 water. There's no such thing as half an oxygen. Oxygen will be O2, so you have to double this to get it to work. And to double it, you need more than 1 electron had a certain number of electrons to begin with, so how many NADH must pass their electrons to the electron transport chain to fully reduce one molecule of oxygen? So you might look at your equation with the cytochrome C and see how many of those it took. And then try to remember how many electrons cytochrome C can hold, and then how many electrons NADH had to begin with. Oh, it's done. Did everybody answer? Here, I'll just restart and move myself fast. Okay. 2 is correct. Okay. So how many electrons per NADH? 2
Two.
electrons. And how many cytochrome C did I need to reduce a molecule of oxygen? 4. So I need 4 electrons, so I need 2 NADH to reduce more oxygen. So, this step requires, it requires 2 NADH to fully, or we can say or NADH to fully reduce 1 O2 molecule. We have now reached the end of the reduction half reaction. So it only took us a month to oxidize glucose, right? Starting with glycolysis, the citric acid cycle. And now we have our reduction part of it, of the redox reaction and the electron transport chain. So that equation, remember, was 6 oxygen plus 24 protons plus 24 electrons. This is the half reaction going into 12 waters. So this is the reduction of the action for oxidation of 1 glucose. How much ATP have we made?
32.
We've made some. How much did we make in glycolysis? It's 1 glucose? 2
2.
How much ATP did we make in the citric acid cycle for 1 glucose?
Including equivalents?
Nope, no equivalents. ATP. Well, okay. ATP, you may count as an equivalent. 2. But we haven't yet used any of the reducing equivalents. To make ATP. Now, we use them to reduce oxygen. So I want to reduce oxygen. And to do what? generated.
Oh. Proton gradient?
What?
Enzymes? Proton gradient?
Proton gradient. Yeah, so that's across the inner membrane of the mitochondria. So that's all we've accomplished so far. We actually haven't synthesized any ATP yet. So 10 protons are transferred to the inner membrane space. For approximately every NADH. Okay, so if we go back to this cartoon figure, complex 1 transfers protons, and it's 4 for every electron pair. Coenzyme Q transfers 4, and that's for every electron pair that passes through it. And then complex 4 passes 2 protons for every electron pair, but you remember when that happens, it's actually 4 electrons going through it, so into an ADH. So the equation I wrote was 4 protons, but only 2 per electron pair. Okay. So that's your 10 protons for every NADH. How many protons are you going to get from FADH2?
2.
6. Yeah, 6. So complex 1 gets skipped and things start here. So you get those 4 and you'll get those 2. So every 6 per NADH, or FADH2, sorry. So 10 protons are transferred to the inner membrane space for approximately every NADH, and this is going to be 6 protons for every FADH2. It takes coupling a proton transport from the intermembrane space to the matrix to synthesize ATP. And it's approximately 3 protons that have to move. Per ATP synthesized. And that's an approximate. So if one NADH moves 10 protons against a gradient, and then we let those protons come back, in an ideal world, how much ATP would we make? 10 divided by 3 is
3.33333.
yeah, about 3 ATP, and that's why when you go into old textbooks, they usually go by the method. They say 3 ATP per NADH. But like we said before, the membrane is not perfect. That transport system is not perfect. We have other processes that consume protons. We lose some of our free energy through heat processes, and so in reality, it's the 2.5 is what you really get from 1ADH. So technically, approximately 3 protons transported per ATP synthesized, and that's where the NADH you get approximately the 2.5 ATP. And the FADH2, which only moves 6 protons, and if you need 3 to make ATP, that is about how many ATP you can make? 2, right? So 6 divided by 3 is 2 ATP. And you go look in old textbooks, and that's what they tell you is 2 because they round it for you, but in reality, it's actually 1.5. That's typically what you get. But I will be showing you how 3 protons are needed to make 1 ATP, and it has everything to do with the structure of the next complex. So we are done with our 4 complexes, but there's actually a 5th one that technically is not part of the electron transport chain, but there's this complex 5 out here that sometimes people lump into the rest of them because it's another complex in the inner membrane. But this is involved in oxidative phosphorylation and the synthesis of ATP, not in electron transport. Okay, that's separate from complex 5. So the very last step is going to take all these protons that got moved into that inner membrane space, and it's going to let them back to the matrix side. We've got a great chemical potential difference in concentrations. We have a great electrical potential difference as well, because we're really positive in that space, more negative over here. That's going to pull those through, which means this is going to be a spontaneous process, and that's where we're going to get the free energy needed to put that phosphate group back onto ADP. So that's what gets coupled to make ATP. So just a couple things about complex 5, and the nuts and bolts we'll get to next time. So complex 5 equals ATP synthase. And this is technically not part of the UTC. This does oxidative phosphorylation. To make ATP. And it uses the proton motive force, which is basically just my chemical and electrical potential energy transport terms. To drive ATP synthesis. This model that we're going to go through is called hemiosmotic theory. And that is basically describes that the energy released in the electron transport chain through my redox reactions is conserved by generating a proton gradient, which is then coupled to ATP synthesis via diffusion of that gradient. Yep. So I got approximately 3 protons must be transported. And again, this is passive now. From the intermembrane space through a complex 5 to the matrix to make 1 ATP. Okay, so then the ATP synthase, we will go through how that is, how that works, which is fun stuff. It's a molecular motor. And have a movie. And then we'll talk about regulation of ATC as well when you're back from spring break.
So this is.
I'm excited for team